Neural networks, a name all too familiar by now, have gained enormous attention in the past few years. In fact, many practical machine learning applications today are based on this amazing idea. But it's not a new concept. The idea of neural networks was already proposed in 1943 by neurophysiologist Warren McCulloch and mathematician Walter Pitts. They attempted to describe how neurons in the brain work by modeling them using electrical circuits, suggesting that the human brain can be thought of as a computing device. However, the first trainable neural network, called the perceptron, was developed by Frank Rosenblatt in 1957. This perceptron was a significant step forward, as it was capable of learning weights from input data. It was a simple linear classifier with no hidden layers, unlike the more complex neural networks we see today. In 1982, John Hopfield introduced Hopfield networks, which are recurrent neural networks capable of serving as associative memory systems with binary threshold nodes. This development renewed interest in neural networks during the 1980s. Following this, Geoffrey Hinton and Terry Sejnowski developed Boltzmann machines in 1985, a type of stochastic recurrent neural network that helped in learning deep representations of data. By the 1980s, researchers developed neural networks with more than one layer, known as multi-layer perceptrons, MLPs. These networks could theoretically solve more complex problems than single-layer perceptrons. The introduction of the backpropagation algorithm by Rumelhart, Hinton, and Williams in 1986 was a breakthrough, enabling effective training of multi-layer networks. However, these early models still faced limitations in computational power, leading to periods of reduced interest and funding in AI research, known as AI winters. In the 1990s, support vector machines, SVMs, developed by Vladimir Vapnik provided a strong alternative for classification tasks, contributing to the evolution of machine learning alongside neural networks. In 1997, Sepp Hochreiter and Eugen Schmidhuber introduced long short-term memory, LSTM, networks. LSTMs addressed the vanishing gradient problem in recurrent neural networks and proved highly effective for time series data and sequence prediction tasks. But then, a hero came and saved the day, the GPU. Graphics processing units, or GPUs, have thousands of relatively small processing units on a single chip. While their architecture is not exactly similar to that of neural networks, their highly parallelized nature makes them perfect for the matrix and vector operations required in neural network training. This development allowed researchers to move beyond the computational power limitations of earlier networks. No longer confined to single-layer networks like the perceptron or even the 2- or 3-layer networks of the 1980s, they could now design networks with many more layers, also called deep neural networks. Around the year 2012, the deep learning revolution truly took off. A landmark event was the success of AlexNet in the ImageNet Large-Scale Visual Recognition Challenge, ILSVRC, which showcased the power of deep convolutional neural networks, CNNs. This success demonstrated the potential of deep learning for a variety of applications, from image and speech recognition to natural language processing and beyond. With the advent of deep learning frameworks like TensorFlow and PyTorch, improved algorithms, large datasets, and advanced hardware like GPUs, deep learning quickly became the state-of-the-art technique for machine learning. Companies and researchers around the world began leveraging deep neural networks to transform industries, automate tasks, and push the boundaries of what artificial intelligence can achieve. Now, this old technique is seen as the cutting-edge technology driving advancements in AI, transforming industries and everyday life. The journey from McCulloch and Pitt's theoretical models to today's deep learning revolution is a testament to the enduring power of human ingenuity and the relentless pursuit of knowledge.